Hey Chem30, welcome. Thank you for being patient for this video to come out. My apologies in its delays. I spent the entire afternoon so far working on making this video. I'm new to making videos, so it took me a while to get the whiteboard set up where I wanted and at a level that I can write on it, and getting a camera position so you can see what I'm doing. And not only that too, learning how to do a video that works and not forgetting things that I need to say, so I have to go back and redo. So this is, I think, trial 5. Anyways, so first things you need to do for this, in order for this to work, is I would go into our D2L in the acid base unit, and you'll find right after ABQ, which is the acid base question set, you'll find this worksheet. And it says Bronsted-Lowry 5-step method practice. So I would go there, download that, and once you've downloaded that, come back for the video. Now, if somehow you've downloaded it earlier this afternoon, make sure that the word sulfate is replaced with fluoride. If you've downloaded it after 2:30, it should already have fluoride there. Okay, so let's get into it. Bronsted-Lowry 5-step method. So Bronsted-Lowry acids, as you've read in the PowerPoint, are a species that donate protons. Bronsted-Lowry bases are species that accept protons. So the Bronsted-Lowry 5-step method is to determine which species in a solution will donate the proton and which species in a solution will accept the proton. Okay, so what is the most likely reaction to occur? So step 1 is you take a look at the species you have and you put them down as they would occur in solution. Sulfuric acid. Well, if you take a look on page 8 to 9 of our data book, and you probably have it memorized already from Chem 20, it's one of our 6 strong acids. Any acid above the gray line is a strong acid. Okay, so let's take a moment and talk about this table before we actually put sulfuric acid down. This is a table of acid-base strength. It's rank ordered from the strongest acids down to the weakest acids. So a lot of students write SA at the top, knowing that this is the strongest acid, and every time you go one acid down, you're getting a weaker and weaker and weaker and weaker acid till you get to the bottom, where you have water, the weakest acid. Now really, the chart starts at the hydronium ion, the gray line, because these 6 strong acids, as soon as they hit water, their first proton immediately leaves them. So they ionize immediately. So they automatically become hydronium plus whatever the second compound is, which is called the conjugate base. So really our chart starts here and goes down, and in terms of base strength, our strongest base is at the bottom, hydroxide, and you work your way up. So our strongest base is here, all the way up to our weakest base at the top, which is water, and these bases here, they're even more weak than water. They're really pathetic that way, because if water is present, which aqueous means it is, these guys are automatically weaker than water. Okay, so this is our acid-base chart. Strongest acid at the top, strongest base at the bottom, and some students write SA, some students write SB. So now, going back to this question, sulfuric acid, is it one of the 6 strong acids? So as soon as it hits water, it becomes hydronium. And, ooh, that's kind of small. Let's make it a bit bigger. That's better. And it becomes its conjugate base, HSO4 1-, aqueous. Second compound, potassium nitrite. So when it goes into water, it dissociates into the potassium ion and the nitrite ion. And this is a solution, so it's got water. Okay, so those are the 5 compounds. That's step 1. Step 2 is to determine if they're an acid, a base, or if they're neither. So we do that determining based on, do they have a proton to donate? Because the Bronsted-Lowry definition of an acid is a species that can donate 1 proton in a reaction, and a base is a species that can accept at least 1 proton. Okay, so an acid can donate at least 1 proton, a base can accept at least 1 proton, and that's how we'll determine it. So I take a look at H3O+, and hydronium, it does have a proton to donate, so I put an A below it for acid. Can it accept a proton? Well, positive things don't normally accept protons. There are some rare ones, and if you're told ever that it's a base, just assume it can accept a proton, whether it's positive or not. But unless you are told it's a base, if it's positive, it doesn't accept protons. So he can't accept a proton. HSO4 1-. He's got a proton he could donate. So we put an acid. Can he accept a proton? He's negative, so he can. So he can be both an acid or a base. Potassium. He does not have a proton to donate, and he cannot accept because he's positive. He's not negative, so he's neither. Nitrite ion. Does he have a proton to donate? No, but he is negative, so he can accept. So we put a B for base. And water. We take a look at water there. Does he have a proton to donate? Yes, and he can also accept. So in this solution, we have 3 species competing to be the acid: hydronium, HSO4 1-, and water. We have 3 species competing to be the base: HSO4 1-, NO3 1-, NO2, nitrite, and water. So let's start with the acid first. What we do is we take our chart and we start at the top and we work our way down, and whichever is the first acid we encounter, that's the strongest acid. So I start at the gray line and, oh wow, hey, hydronium, right there. So this is my strongest acid present. So I put an S. Okay, the other 2 acids won't react as acids because hydronium is present to be the strongest acid. Now, I start at the bottom and work my way up to find which is the 3 is my strongest base. So I start working my way up and working my way up and working my way up and keep going, and oh, here we go, nitrite, NO2 1-. So it's my strongest base present. The other 2 bases, water's here and HSO4 1- is here. So they are weaker than nitrite, so nitrite is my strongest base present. So now the next step is we write a reaction in which the strongest acid present donates 1 proton to the strongest base present. Now I say present because that being the strongest acid or strongest base in a Bronsted-Lowry 5-step method question doesn't mean you are truly a strong acid or base. Hydronium is a strong acid. Nitrite is not a strong base. But in terms of those species present, this is my strongest base present. This is my strongest acid present. So my reaction is hydronium donates 1 proton, because it's the strongest acid present, to the base, which is nitrite. So that'll be those are my reactants. My products, and I'll write in my double-headed equilibrium arrow, will be H2O, liquid, and HNO2, aqueous. Okay, so my reaction is strongest acid, donates 1 proton to strongest base. So our products are water and HNO2. Now, we need to determine extent reaction. As you read in the notes, what we do is we take a look and you find your acid and you find your base. If your acid is above the base, let's say that my acid was the phosphoric acid. Here's my acid, we'll say. And let's say that benzoate was my base. I would go from my phosphoric acid down to the benzoate, and since it is going downhill from the acid to the base, I would call it greater than 50%, and I'd write that above the arrow. If instead my acid, let's say I'm using propanoic acid, is below my base, let's say I have F-, so I go from propanoic acid, well, there we go, upwards to my base, that would be less than 50%. And the way I think of it is if I'm standing at the top of a ski hill, I got skis on, and someone gives me a little bit of a push, there's a better than 50% chance I'm going to go down the hill. If instead I'm at the bottom of the hill and someone gives me a little push, I would say there's a less than 50% chance I'm going to automatically ski up the hill on my own. Okay? So going downhill is greater than 50%, going uphill is less than 50%. Now, we have a special situation when either hydronium or hydroxide are present. Why? Because they are so strong. Hydronium is so strong at giving away a proton, and hydroxide is so strong at accepting a proton or stealing it, that instead we would say it's not greater than 50% or less than 50%. We would say it's greater than 99%. That's the extent of reaction. It is so powerful. Now that's one way to write it. The other way, when you have hydronium or hydroxide, is to change the arrow to a quantitative arrow, which says that these two react and they make products. They don't really go backwards at all because it's such a powerful reactant. Okay? There's my 5-step method. So what I did is I put all species present down. I determined if they're acids or bases. Then I determined which is my strongest acid present using my chart, strongest base present using my chart. Then I had my strongest acid donate 1 proton to the strongest base. And then I created my products. And then I determined if my acid was above my base or acid was below the base and put an extent reaction in. That's your 5-step method. So this is the most likely reaction that would take place in this solution. So what I recommend you do now is pause the video, try the next question on your own, and then after you've tried it, start the video back up and you'll find me solving it with you. Okay, we'll see you in a few moments. Welcome back. So hopefully you've had a good chance, a good opportunity to try practicing that second question. So let's go through it together. A solution of sodium dihydrogen phosphate, so sodium Na+, dihydrogen phosphate, H2PO4, 1-, is added to a solution of potassium, K+, fluoride, F-, and it's a solution, so water is present. Okay, that was our first step. Second step, determine acids and bases. Sodium ion does not have a proton to donate, so it can't be an acid. It is not negative, so it can't accept, so it's not a base, so it's neither. H2PO4 1-, it does have a proton it can donate. It's negative, so it can accept a proton, so it's also a base. And since it can do both, donate and accept, we call it amphiprotic. Amphiprotic means it can donate a proton and also it can accept a proton. So it's a special compound, it's both an acid and a base. K+, does he have a proton to donate? No. Can he accept? No. So he's neither an acid nor a base. Fluoride ion, does he have a proton to donate? No. He's negative, so he can't accept, so he's a base. Liquid water, does it have a proton to donate? Yes. Can it accept? Yes. So it's also amphiprotic. It's a compound that can accept or donate. Now, we take our chart and we determine which of the two compounds competing to be the acid is the stronger compound. And so I'm going to start at the top, start working my way down the chart. So I start the hydronium ion, work my way down, work my way down, work my way down. Oh, there's the dihydrogen phosphate ion. And there's water. So the dihydrogen phosphate ion is higher than the water, so it's therefore the acid. So I'm going to put S in front to indicate strongest acid present. Now, I have three compounds competing to be the base. So he's the acid, but he's also competing to be the base. We start at the bottom at hydroxide, the strongest regular base possible. We work our way up, and we keep going, and keep going, and keep going, keep going, and wonder why Clemmer did this to us. And then we get up here and we go, oh, F-. He's the first of the three bases. There's my H2PO4 1-, and there's water. So F- is going to be my base. So he's the strongest base present. Now, we write the reaction as strongest acid present donates 1 proton to strongest base present. So I write H2PO4 1- aqueous plus F- aqueous. We put a double-headed arrow in, and those are my two reactants. So my strongest acid is going to donate 1 proton to my strongest base. So let's go do that. So we take 1 proton off, that gives us HPO4 2-, and the F-, when he gains a proton, he becomes HF aqueous. Okay, so strongest acid donated 1 proton to strongest base, and those are our products. Now we need to determine extent reaction. So once again, I take my chart, and I find my H2PO4, 1 minus, which is my acid. So he's here, and so you can put one finger on that. F minus is my base, he's up there. So I will be going from my strongest acid uphill to my strongest base. Therefore, it's considered to be less than 50% chance to occur. So in this situation, we'd have more reactants than we would have products. So less than 50% for the extent of reaction. So there we go at our 5 steps. Species put down that are in solution, label them as acid or base, determine strongest acid, strongest base present, go ahead and write the reaction. Strongest acid donates 1 proton to strongest base, determine extent reaction. Okay, so what I recommend you do is pause the video, try number 3, which is hydrofluoric acids added to a solution of potassium acetate, and once you've done that, start the video back up and I'll solve it with you. This is so weird talking to a phone, not talking to real people. Well, I guess you are real people, but talking to you guys live. This is just weird. Okay, back to this. Hydrofluoric acid is added to a solution of potassium acetate. Well, hydrofluoric acid, I look on my chart, it's one of my weak acids, so it does not ionize when it goes into solution. So it stays as HF, aqueous. I'll make that a little bit bigger for you guys. Potassium acetate, so we have the potassium ion, and then we have acetate, CH3COO minus, that's aqueous, so all 3 are aqueous, and then, it's a solution, we also have liquid water. Okay, so now, we have all species as they would occur in solution. Determining acid and base. HF, does it have a proton to donate? Yes. So we put an A. Is it negative so that it can accept a proton? No, it's not negative, so it's not a base. Potassium ion, does he have a proton to donate? No. Is he negative so he can accept? No. So we put a dash. The acetate ion, does he have a proton to donate? Well, he has 3 hydrogens, but they're not the acidic hydrogens. Those are not donatable. The hydrogen that would be at the end if it was acetic acid, that's a donatable ion. Okay? And when we do organics later on, we'll talk about the actual structure of acetate. Just realize that for the organic acids, the donatable hydrogens at the end of the COO end. So COOH, we'd have a donatable proton. COO negative, we do not have a donatable proton. So he can't donate. Can he accept? Well, he is negative, so he's a base. Water, as you know, he can both donate and accept. So he can be in either an acid or a base. So now we have 2 compounds competing to be the acid, 2 compounds competing to be the base. So once again, we start at the top where the hydronium is. We work our way down. And this time, we don't have to go too far. Clemmer picked one that we could travel and do a little bit less work with. It's hydrofluoric acid, HF. So, hydrofluoric acid, strongest acid present. Now, we've got 2 competing to be our base. We start at the bottom. At the hydroxide, we work our way up. And once again, Clemmer picked one that's not as far away. And we have it right here. Where is it? Just lost it. Oh, here it is. CH3COO minus. So here's the acetate ion. And there's water way up there. So the acetate ion will be our base. So our strongest base in this situation is CH3COO minus. Okay, so now we write the reaction. Strongest acid donates 1 proton to strongest base. HF aqueous plus CH3COOH. Oh, he's not H, he's not yet. Minus aqueous, double-headed arrow, becomes, so when he donates 1 proton to him, he becomes F minus. And he gains a proton, so he becomes CH3COOH aqueous. Okay, so he donated one proton as the strongest acid to the strongest base, making F- and CH3COOH. Now, let's determine extent of reaction. So we find our acid, and our acid, HF, is here. We find our base, he's here. So going from here to here is downhill, so we know it's greater than 50%. So with the greater than sign, 50%. So I put down the species present, determine acids and bases, determine strongest acid present, strongest base present, wrote a reaction where strongest acid donated one proton to strongest base, and then using my chart determined if it was greater than or less than 50%. All right, so I'd recommend pausing the video at this point and coming back once you have tried the fourth and final situation. Hey, welcome back. Let's go ahead and let's try this one. Hydrochloric acid. Okay, hydrochloric acid. I look at my chart, and he's one of the 6 strong acids, so as soon as he hits water, he ionizes. He becomes H3O plus and Cl minus. Then it's added to a solution potassium acetate. Oh, we got acetate again. K plus, and we have acetate, CH3COO minus, and it's a solution, so we have water. Okay, once again I use my chart, I've determined if they can donate or accept. Hydronium, he can donate a proton, he's positive, so he can't accept. Chloride does not have a proton, so he can't donate, he's negative, so he can accept. K plus, he's positive, no proton, so he can't donate a proton, and he can't accept, so he's neither. Acetate ion, once again, these 3 hydrogens are not donatable. If there was one, it would have to be at the end there. So there's no donatable proton, so he's not an acid, but he is negative, so he can accept, so he's a base. And our final compound, water, has a proton to donate and can accept. Okay, so now we have 2 compounds competing to be the acid, 3 to be the base. So once again, we get our chart. We start at the hydronium ion, and well, that's the first contestant, so hydronium wins. And if you take a look, the other acid, water, is like right at the bottom. So first contestant, hydronium wins. He's the strongest acid present. So you've probably already figured it out. Whenever hydronium's there, he's the strongest acid present. And just like if hydroxide is there, which is at the bottom of the chart, he's the strongest base. You've already determined them. Okay, now we've got 3 compounds competing for the base. So once again, we start at the bottom, work our way up. And there's the acetate ion, so he is the strongest base present. If we were to keep going just to check it out, water is here, Cl minus is here. So our acetate ion is our strongest base present. So now we rate the reaction. The strongest acid, H3O plus, donates 1 proton, so we react it with CH3COO minus. And since anyways, we'll write double-headed arrow. So he reacts to give him 1, so he becomes water. And he becomes CH3COOH aqueous. So strongest acid present donated 1 proton to strongest base present, making the following products. Now, let's take a look at this. Extent reaction. Well, our acid is above our base if we look at our chart, so it would be greater than 50%. So if I look here, my acid is above my base. So it would be greater than 50%, but since hydronium is present, that makes it a special situation. It's considered to be a quantitative reaction. So we either write greater than 99%, or we replace it with a quantitative arrow. So that's one way to represent it. Or the other way is to put a quantitative arrow in. And we have that. So there's our 5-step method video. So please go back and practice. I would do some more. decide how many you're going to do. There are questions at the bottom of the first page of the question set that I gave out, or that is actually, sorry, in the D2L shell. So if you haven't done so yet, you can download it. The top question set there simply goes through and gives you an opportunity to determine, is it an acid or a base? And I'd skip the second set of questions and just jump onto the bottom where it says Bronsted-Lowry 5-step method and go through, and there's an answer key available on D2L for you to check your work to see if you're doing it right. Sometimes I think I may have skipped putting states in, so my bad. So I should have states in there always, and it should be fully labeled like this. Okay. Anyways, if you have questions, we'll have our tutorial Monday at 1 p.m. Sorry, at 11 p.m. 11 a.m. Not doing it. Not doing it at 11 p.m. Okay. Thanks. Bye-bye.